In this section, let's continue with the summary. We are going to obtain the confidence interval for my sample, my population mean. We have a population. In this population, we have a mean, but we don't know this mean. Also, we don't know the standard deviation. Then, to estimate this mean, we are going to select one sample. If this sample is big enough and is a representative sample, when we compute my sample's mean, this statistic will be very close to this parameter. My best guess in this case will be X bar, plus or minus an error. Then actually this confidence interval is X bar minus the error and X bar plus the error. Then I expect to catch the true proportion with this interval. That is the idea, because this value is close to this value. Then my problem is, how can we find this error? How can we find this error? Then in the previous chapter, we studied that if my sample size is greater than 30 units, doesn't matter what is the distribution of all individual values. Could be something ugly like this. Suppose that I know the mean and the standard deviation. The distribution for all samples means the distribution of all these values. X bar 1, I will select all samples of the same size, all samples of the same size, all of them, all possible samples. Then X bar 2, I will compute the samples mean for these samples, X bar 3, and so on. The distribution of all of these values follow according to the central limit theorem, a normal distribution. And what is the center of the distribution? The center of the distribution will be the true parameter. The mean of all samples mean will be the true parameter. The mean of this value plus this value plus this value plus X bar 4 and so on, when we add it and divide it by the total, the mean of all of this value should be the true parameter. That is the value in the center of that distribution. And what is the standard deviation of the distribution? Will be given according to the central limit theorem, the standard deviation of the population divided by my sample size. The bigger is my sample, the smaller will be this standard deviation, the skinnier or the narrower will be my distribution. If my sample size is so big, then I am expecting that the distribution of all samples mean when my sample size is very big, the center will be the same, the true mean of the population, but the distribution of all samples mean will be narrower, will be skinnier. That is the distribution for all samples mean, and we are going to transform, because we are going to solve this problem using table. We need to transform this distribution in the standard normal distribution. What is the standard normal distribution? We need to obtain the C-score of all of these samples, the C-score for the sample, the C-score for the sample, and so on. Remember, each of these samples are represented by 1 point. Suppose this sample is represented by this point. And what is the C-score for this sample? The mean for this sample is given in this number line, for this number located in this scale. That is my sample's mean. How can we obtain the C-score of this sample mean? How far away is this value from the center? Is given by this formula. X bar minus the center of this distribution is the true parameter. And what is the standard deviation of this distribution? Is this one, is sigma square root of n. But really, it's very strange that we know the standard deviation of the population when we don't know the mean of my population. However, when my sample size is bigger than 30, then the standard deviation of the population could be approached with the standard deviation of my sample. Then we can substitute in my C-score. When I have a sample bigger than 30, I can substitute the standard deviation of the population with the standard deviation of my sample, and that is the formula that we are going to use to obtain the C-score of any sample in this population. And the distribution of all these C-score follow a normal distribution, remember, all samples located here, all of these samples, each point represents one sample, one of these samples. Then all of these samples have a samples mean equal the true parameter. Then the C-score for all of these samples located here the C-score will be 0. Then how can we obtain the error? This error depends on basically my sample size, but also depend on my confidence level. Suppose that my confidence level is 95%. I expect to select any of these samples located here. We have 95% of all samples located here. This distribution is equivalent to this one, that distribution for all samples mean. Samples mean, exactly. Then this is 95% of all samples. Then these two areas are equivalent. Then if I find the C-score of these 2 points that represent the C-score for this value also, these two C-scores represent my critical values. And the critical values are denoted by this symbol, Z alpha half and negative Z alpha half. Why Z alpha half? Because if we have 95% confidence interval, then alpha is the complement. Alpha should be 5% and alpha half will be 2.5%. Then alpha half is the area located here. Then this point, if this area is alpha half, then this score should be Z alpha half. Then because this area is equivalent to this area, this point is located Z alpha half standard deviation to the right of the mean. Then the maximum error in that distribution will be given by this distance. And the maximum error is given by this distance. That is my maximum error, this distance. How can we obtain this distance? It's the distance between the center and this point. And this point is located Z and a half standard deviation from this point. Then the error should be given by this formula. Z alpha half, the number of standard deviation that this point is located from here, times the standard deviation. The standard deviation of the distribution is given by sigma square root of n. And remember, if my sample size is greater than 30, I can use instead the standard deviation of the population, the standard deviation of my sample. And that is the formula that we must use to obtain the confidence interval for my population mean. But we have studied only case when my sample size is bigger than 30, it's a big sample. What happens if we have to obtain the confidence interval when my sample size is not so big, it's smaller than 30? Then in those cases, we have a population and the mean of the population is mu. We don't know it. To estimate this value, we select a sample and we compute in this sample my X bar, and we don't know also the standard deviation of the population. Then we need to compute the standard deviation of my sample. And we know that if, in the previous chapter we studied, if the distribution for all individual values follow a normal distribution, if the distribution is the distribution for individual value, the mean is mu and the standard deviation is sigma. When the population have this distribution, doesn't matter what is the size of my sample, could be small or could be big, the distribution for all samples mean follow a normal distribution, but the population must be normal. Then the center of the distribution will be the true parameter. The mean of all samples mean is the true parameter, and the standard deviation will be the standard deviation divided by a square root of n. But we don't know the standard deviation of the population, but we can transform that distribution in the C-score or T-score distribution. We can transform this in the C-score when we know the standard deviation. If we know the standard deviation, we can transform this in the C-score, and the C-score for each sample is obtained by X bar minus the center divided by a square root of n. And we can transform this in the standard normal distribution, but this is indicate that sigma is known. But this case is very strange. How can we know the standard deviation if we don't know the mean of the population? It's very strange. Then the common case, also the actual case in reality, is when we don't know the standard deviation. Sigma is unknown. Then when sigma is unknown, we have a problem. We need to transform this distribution in other distribution that we can use to solve the problem. The distribution that in which we are going to transform that distribution will be a T distribution. T distribution. How can we compute this statistic, T-score? It's very similar to this statistic, C-score. but instead z-score, we are going to obtain t-score. And will be similar. For example, if we select this sample, and this sample is represented by this point in that distribution, because that is the distribution of all samples mean, then the mean of this sample will be x bar, and the t-score for this bar will be obtained in this way: x bar minus the center, which is mu, divided by the standard deviation. But the standard deviation of the population is unknown. We need to use the standard deviation of my sample. Then we substitute this standard deviation for the population standard deviation in this formula. The z-score is different to the t-score, and the distribution of the z-score is normal, but the distribution of the t-score look like a normal distribution, but it's not normal. The distribution look like this. I am exaggerating a little bit. And that distribution received the name of t-student distribution. T-student distribution. Then this is a t-student distribution. The difference between these two distributions is that the tail of this distribution is thicker, both tails are thicker and longer. And in that distribution, we know in the normal distribution that between -3 and +3, this 0 is located in the middle. Actually, the t-score of all samples located in the distribution here, remember, all samples, that is a sample, the mean of all of these samples are equal to the true parameter. And the t-score of all of these samples, when we substitute x bar by mu, we will obtain 0 for all of these samples. The t-score of all of these samples will be 0. And the distribution of all z-score of all of these samples will be between -3 and +3. However, when we compute the t-score for the same sample, the t-score is more spread about 0. Could be between -10 and +10. Could be between -5 and +5. Here, 99.7% of all of this sample, the z-score will be between -3 and 3. Samples mean. And however, the t-score are more spread. Why is more spread? Because in the formula for the t-score, we have two variables: the samples mean and the standard deviation corresponding to the same sample. However, in this formula, the only variable is the samples mean, because the standard deviation that we use in this formula is the standard deviation of the population, but that we don't know it. Then, how can we obtain the confidence interval for this parameter? If this sample is a representative sample, doesn't matter that it's small, we are going to compute the confidence interval for the true mean is given by my best, because I will use only one sample to estimate this parameter, only one sample. Then I will compute this and this. Then will be this value plus or minus the error. It means that this value is close to this true parameter. Then the confidence interval will be x bar minus the error and x bar plus the error. I expect to catch the true parameter with this confidence interval. But my problem is the error. What is the formula for the error? Look at this. In that distribution, in this distribution, we are going to use the same concept for confidence level. Suppose that this is a 95% confidence level, and this is equivalent in that distribution to this 95% confidence level. And the maximum error here is given by this distance, and is this value, the t-score for one sample located here, the t-score is exactly this t-score. This t-score, then this t-score is t alpha half, and this is negative t alpha half. Why? Because this area should be alpha half, and this other area should be alpha half. When my confidence level is 95, alpha should be equal 5% and alpha half should be equal 2.5%. We can find this value using table or using StatCrunch. And I know that the t-score for this sample is exactly this t alpha half, and the distance, this is my maximum error. Then the maximum error is given in this formula for this expression, the maximum error. Because we are going to use t-distribution, we need t alpha half times the standard deviation, but because we don't know the standard deviation of the population, we have to use the standard deviation of my sample. We are going to use this formula when my sample size is smaller than 30 and the population is normal. When my sample size is bigger than 30, remember we are going to use Z, normal distribution. Normal distribution because we can approach sigma with my sample standard deviation. That is when n is greater than 30. But when n is smaller than 30, we need this condition. My population should be normal and we are going to use t-distribution. And we have to use this formula to obtain my confidence interval. That is basically the summary of this chapter.